So moving into part 2 of our chapter 14 notes, we're going to cover some probability, a couple examples, and then get you out of here. So last time we focused on theoretical probability to finish up the notes. Now we're going to focus on empirical probability just for a little bit. So for each of the previous cases, we can find an empirical probability by actually doing the experiment repeatedly and counting the number of times we get the desired result. Like if I wanted to, I could give you guys all die and you can roll them and roll them and roll them, and we can see if we get the sum of 4. And how likely is that? The probability of rolling an even sum on a pair of dice, we roll a pair of dice many times and count the events. So the number of times we get it divided by the number of attempts is our probability. So given the frequency distribution on the right, what is the empirical probability a person will be sick for 3 days? So I want to know, what's the probability someone's sick for 3 days? So if I look on this and notice that all of these employees that are absent sums up to 100. I've got 28 that are sick for 1 day, 5 that are sick for 2 days, 4 that are sick for 3, and 3 that are sick for 4. So I have 4 out of 100, or 1. That is not 1/4, Mr. Swenson. That would be 1/25. If I asked you, what's the probability a person will be sick for 2 days or fewer, it's just really asking you, what's the probability that is less than or equal to 2 days? So less than or equal to 2 days would be 60 plus 28, that would be 88, plus 5, which would be 93, over 100 total sick days. So we take the number in our event that we want, 93, over the number of attempts, 100, and we get 0.93. I want you to recall the first 3 rules of statistics. I said it before, I will say it again. Those rules also apply to probabilities. So our idea is to make a picture, and make a picture. So we could list the sources, or all of the possibilities out. We could use a tree diagram. The next thing that we're going to see is a Venn diagram. We could also see a frequency table. And all of those are equally valid ways of displaying. So a common kind of picture that is very useful is a Venn diagram. I hope many of you have seen this. We are going to practice this in class. A second very useful picture, or graphic organizer if you want to call it, is the tree diagram that we've seen. And a third possibility is a two-way table, those contingency tables that we have seen when we're comparing multiple events. This especially allows us to see conditional probabilities. So notice these are not mutually exclusive. New term that we need to know what that means. So let's say we're finding the sample space for the gender of 4 children and we want to make a tree diagram. Well, we can look at our tree diagram and walk down each branch of the tree and go boy, 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 boy. We get our first idea, or our first piece in our sample space. And then we go boy, girl. Sorry, we can go boy, boy, girl, boy, 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 girl, girl. And we get all of our lists and seeing that we get 16. If we're using a Venn diagram, this is more when you know that there's overlap. For example, suppose we have 38 students in this class and 20 students are a male. That's not true. Also, let us assume that 24 of the students have pierced ears and 8 males students have pierced ears. Oh, interesting. So if we wanted to see this comparison as opposed to looking at a two-way table, we have the number of males, we said was 20. We have the number of people that are pierced, which is 24. And we have the number of people that are male and pierced. Remember, this means and is 8. So what I highly suggest is you always start with the overlap first. So we know that there's 8 males with pierced ears, which means that there are 12 males that don't have pierced ears. This is male and not pierced. Or we have 24 people that have pierced ears. We've already counted 8. So that means there are 16 people that are pierced ears that are not male, also known as female. if you add each of these up, we have 20 plus 8 plus 24. Sorry, if we add these up, 20 plus 24, that's 44. We know that's too many people because we only have 38 people in the class. So this is double counting this 8 if you just added up those numbers, which is oftentimes what people end up doing. It's not right. So what we want to do is say 12 plus 8 gives me 20, plus 16 is 36, which means I have 2 females in the class that don't have pierced ears. So that's the Venn diagram way. The other contingency table way, and remember what we call these marginal distributions. Those are our margins. We have a total of 38, so our sum should match up. I have 8 male, 16 female, total of 24 students. I have 12 male not pierced, and I have 2 females that are not pierced. If I go down, I have 20 males, means I also have 16 females. I have 24 pierced if I go across, and I have 14 not pierced. Either way, we go 20 plus 18 is 38, or 24 plus 14 is 38. Gives me my total. Or a third way would be our tree diagram. So we have 38 students. We have 20 male, 18 female. We have 8 males that are pierced, which means we have 12 males that are not pierced. Total of 20. We have 16 females that are pierced. We have 2 females that are not pierced. 3 different representations of the exact same question. So then once we are able to count the different ways, then we can ask the interesting probability questions. Like, what's the probability you choose some student at random and that they're male? Well, that'd be 20 out of 38. Or what's the probability that someone has pierced ears? That would be 24 out of 38. You can see that the Venn diagram might be helpful for some of these, or the contingency table might be helpful for other of these questions. It all depends on how you see the information. Things I want you to start noticing is the probability of male or pierced. Not male, we use a little squiggly. That means not male, which is also on the previous slide. Not male or pierced means the probability of male and not pierced, which is 2 out of 38. I will gladly go over all of these if you want, but I'd rather do that with the examples that we work on in class. The idea is first figuring out the sample space of each and then being able to tabulate what the probability is asking. No, we're introducing some new symbols. So if you see this means probability of not A. We can see the same probabilities from the tree diagram. So what's the probability of picking a male? It would be 20 out of 38. What's the probability of pierced? Would be 8 plus 16 out of 38. What's the probability of being not male? Well, that means female, which would be 18 out of 38. So whichever way you choose to visualize, you're going to get the exact same answers to these questions. Okay, the third way. How about with the table, which is most likely how you're going to visualize a lot of the probabilities that you're given, is this two-way contingency table. What's the probability of being male, which would be looking down on the column male. What's the probability of male and pierced? So we go male and then pierced, and we get this 8 value, 8 out of 38. Remember, we're always comparing to the sample space. What's the probability of being male or pierced? Well, we have 20 males that are, or 20 that are male or pierced. Well, we also have to include the 16 females that we didn't count for, which would give us 36 out of 38. So 3 different ways of visualizing the same thing. When we're dealing with probabilities, The probability is always going to be a number between 0 and 1. If the probability is 0, it will never happen. If the probability is 1, it happened. For any event, A, it has to be between these two numbers. That bears repeating because some people really don't get this. Probabilities will always be between 0 and 1, no higher, no lower. Think of it like a scale. If you're talking about probabilities, if you're closer and closer to 1, it's more likely, or if you're at 1 or 100%, it's certain to have happened. As you get closer and closer to 0, it's more likely than not to have not happened, or if you're at 0, then it's impossible. So think of probability as this sliding scale. If we're talking about formal probability here, this is more of the probability assignment rules. So the probability of a set of all possible number outcomes of a trial must be 1. Let me say that again. The probability of the set of all possible outcomes, if we're looking at everything, it has to be 1. So the probability of the sample space happening is 1. S represents the set of all possible outcomes, or what we call the sample space. Notation matters, right? Probability of the sample space happening is 1. You're in there. If we're talking about the complement, there's 2 ways to say the complement. It's not like very nice job. No, the complement with set notation means a thing. It means not that. So the set of outcomes that are not in event A is called the complement of A, denoted as A of C, or squiggly line A, or not A. The probability of an event occurring is 1 minus the probability that it does not occur. So if we know what the probability of A is, then the probability of not A is 1 minus probability of A happening. Oftentimes, it's easier to calculate complements than it is to find the big sum. Again, we will practice that. Next up, nice big term here, is mutually exclusive events. Events that have no outcomes in common and thus cannot occur together, we call disjoint or mutually exclusive. These are 2 things that don't have anything in common, often confused with independent. Don't confuse them with independent. So the probability of A or B happening is the probability of A plus the probability of B. Or more specifically, the probability that A and B happen is 0. There is no overlap, which is often easier to visualize with a Venn diagram. If we're talking about or, and we know that the events are mutually exclusive, the probability that one will occur or the other will occur is the sum of the probabilities that each will occur. So if I flip a coin and I roll a die, what's the probability of getting a head or a 6 would be 1 out of 2 plus 1 out of 6, which is 4/6 or 2/3. The probability of rolling a 1 or a 5 is 1/6 plus 1/6. There's no 1/5 that could happen. We get a 1, we get a 5. Our notation, as I've been trying to hint at, now here is formally in the notes. In our textbook, they use the notation probability of A union B, which means or, and P intersect B, probably A intersect B, which means and. In other situations, you might see the following: probability of A or B instead of A union B, or probability A and B instead of A intersect B. So do not confuse independent with mutually exclusive. Please make a note of this. We are not going to do this. Mutually exclusive events are not independent. Mutually exclusive means events have no common outcomes. Independent means the probability of one event is not influenced by the outcomes of the other event. So having no relation doesn't mean that one is influenced in the other. Keep that in mind. And number 4, with our addition rule. For 2 disjoint mutually exclusive events, the probability of A and B, or the probability that one or the other occurs is the sum of the probabilities of the two events. So for two disjoint, we have the probability of A or B is probability of A plus the probability of B, provided that A and B are mutually exclusive. Flipping a head or a tail would be 1/2 plus 1/2. Probability of rolling an even number or a 5 would be 2, 4, 6. Those are our evens, 1/2 plus 1 out of 6, which is the probability of 5, which gives us 4/6. If we're talking about and, or means add, and means multiplication. For two independent events, A and B, the probability that A and B, and requires both to occur, it's more exclusive, is the product of the probabilities of two events. So probability of A and B is equal to the probability of A times the probability of B, provided A and B are independent. Again, one does not influence the other. For example, flipping two heads on two coins would be 1/2 times 1/2, or 1/4, as we saw in our diagram. The probability of rolling snake eyes, which is 2 ones, is the probability of getting 1 out of 6 times the probability of 1 out of 6, or 1 out of 36, which we could see in multiple different visualizations. With our multiplication rule with and, two independent events, let's call them R and C, are not disjoint if the two events occurring together has probability greater than 0. Do not be too quick to assume independence or mutually exclusive. In fact, assume neither is true until verified. So we can't just assume two things are independent and multiply them. We can't just assume that two things are mutually exclusive and just add them. There may be some overlap that we need to take into account. So I'm going to say this one more time. Two independent events are not disjoint, meaning there's some overlap, if the two events occurring together has a probability greater than 0. So putting the rules to work. Most probability problems work with the combination of these probability rules that I've just described. Many probability problems do not involve independent events or mutually exclusive events, but we'll save those for the next chapter, okay? Let's just keep it simple. Whenever you see the words at least, ooh, this AP loves this. At least you should always think complement. It may be a ton easier to work with the complement of an event than to work with the multiple possibilities indicated by at least one. Well, what's the complement of at least one? None. Let's finish this out with a problem. There's 3 slides left and then we are done. So suppose that 40% of cars in our area are manufactured in the United States. 30%, so let's write these out. Probability of US is 0.4. Probability of Japan is 0.1. Probability of Germany is 0.1. And probability of others is 0.2. If cars are selected at random, find the probability. A car is not made in the US. Well, if we're talking about not US, then that's simply saying what's the probability of being made in the US? We said 40%. And we do 1 minus that, 0.6. That's different than adding up each of the others. Nope, 31, yeah. You can do it either way, but you can see how complements are useful. What's the probability a car is made in Japan or in Germany? So note, a car cannot be made in 2 places, which means that they are mutually exclusive or disjoint. So the probability of being made in Japan or Germany is just probability of Japan, which we said was 0.3, plus the probability of being made in Germany, which is 0.1. So a total of 0.4. Same setup. We have our probability of US is 0.4. Probability of Japan is 0.3. Probability of Germany is 0.1. Probability of other is 0.2. Oh, okay. What's the probability the next 2 cars you see are from Japan? Well, we can assume that cars driving down the street, one's not influenced by the other. So if you see a car driving down the road, the person in front of him is like, oh, I got to get that car. That's kind of not how it works. So we can assume that they're independent events. So we would multiply these two probabilities of 0.3 times 0.3, which gives us 0.09 or 9% chance. If I ask you what's the probability the next three cars are not from Germany? So I'm saying, what's the probability of not German and not German and not German? So each of those is independent. Probability of being not from Germany is 90%. So we multiply each of those not from Germany's to get 0.729 or 72.9%. Same numbers. If I asked you what's the probability of at least one of the next cars is from US, I need you to think in complements. So independent events, yes, they are independent. At least think complement. So if we have three cars driving by us, what's the probability if they're at least one of the next three cars is from the US? Think not US for all three. If it's not US and not US, then not US, I get probability of 0.216. Well, at least one US car would be 1 minus the probability that we just found. So the probability of getting at least one US car in three cars driving down the street in Dearborn would be 0.784, 78.4% chance. Again, the first car we see is, the first Japanese car we see is the fourth car. So what we need is, what's the probability of not Japan, not Japan, not Japan, then Japan? Or 0.7 times 0.7 times 0.7 times 0.3. And once you're able to assemble these and practice with these probability rules, especially the complement rule, it will become easier for you. There's a lot of known probabilities. So we live in a world of what are actually irrational fears. So like fear of a child kidnapping or candy poisoning or a terrorist attack or immigrants. If terrorists pulled off a 9/11 every year, your probability of being a victim would be 1 in 100,000. That's infinitesimal. The probability of you dying in a car accident this year is 1 in 6,500. The probability of you being murdered is 1 in 16,500. And the probability of dying in a crosswalk is 1 in 48,500. These totals come from the Bureau of Labor Statistics. These are known, yet our brains think and see an example, an anecdote, and want to be able to describe all situations in this type of fearful way. So my goal is to educate you and give you a better idea of how to think in probabilistic terms. I know I'm going to not succeed at this, but the goal is to work at it and to practice it. So I will see you in class. We're going to work through these problems, and I hope to see you in the next one, Falcons.